I'm excited to announce today that Dr. Michael Gion and his team have used our Spitzer space telescope to determine that there are actually 7 Earth-sized planets orbiting the nearby TRAPPIST-1 star about 40 light years away. 3 of these planets, marked in green, are in the habitable zone, where liquid water can pool on the surface. In fact, with the right atmospheric conditions, there could be water on any of these planets. So for the first time, we found as many terrestrial planets around a single star. The discovery gives us a hint that finding a second Earth is not just a matter of if, but when.
As technology increasingly brings the deep cosmos within spying distance, we can now turn our eyes to the most unlikely of places, in the hopes of answering one existential question. Are we alone?
When I was a student, we knew about 9 planets. That was it. What we can say today is that statistically, there are more planets out there than stars. Every star has 1 or more planets.
Planets orbiting stars that are not our sun are known as exoplanets. And NASA has just made a groundbreaking discovery of multiple Earth-like exoplanets surrounding a single star. This cosmic jackpot wasn't discovered overnight. 2 years before NASA's announcement, scientists at the European Southern Observatory pointed their telescope 39 light years from our solar system and confirmed a new star, now known as TRAPPIST-1, as well as 2 Earth-like exoplanets in its orbit. But it wasn't until NASA's Spitzer telescope was aimed at the system that an additional 5 exoplanets were confirmed.
TRAPPIST-1 is an ultra-cool dwarf, and that means that it's much brighter in the infrared, thousands of times brighter in the infrared than in the visible. So it makes it ideal to use Spitzer, which is an infrared telescope, to do the follow-up on this system. So we don't image the individual planets. What we do is the planets pass in front of the star. We see the amount of light that the star is dimmed by when that planet is blocking it. So the dips you see in this animation are the planets going in front of the star, blocking a little bit of the light. The size of the dip tells you the size of the planet. Now, when you see the different planets, they keep orbiting around, and every time they transit, you can measure the spacing between the transits, and that tells you about the orbit, the period of the orbit, how long that year is. And with that, measuring those differences, what we're able to do is measure the masses of the planet. So now we have the mass of the planet, the size of the planet, so we can make an estimate of what the density of the planet is. And that's important because that gives us some understanding about what the composition of the planet is. We also know the distance it is from the star, and that also tells us whether or not it's in the habitable zone.
Spitzer has been able to determine that the closest planet, TRAPPIST-1b, orbits its star every 1.5 days. The farthest, TRAPPIST-1h, completes its orbit in roughly 20 days. And the planet's size is between 75 to 115% of our Earth, indicating they could all be rocky bodies.
The planets, 3 of them which are in the habitable zone, so also called the Goldilocks zones, where liquid water could exist. Having 3 of these Earth-sized planets in this habitable zone is very promising for the search for life beyond our solar system. And for one of them, our measurement is precise enough to strongly suggest a water-rich composition, which is very exciting because this is one of the planets in the habitable zone. These planets are orbiting so close to the star that they must be, or they are probably, tidally locked, which means they always face the star with the same side, like the moon, to the Earth, with a permanent day side and a permanent night side. Now what is also exciting here about this system is that the planets are so close to each other. If you were on the surface of one of these planets, you would have a wonderful view on the other planets. You wouldn't see them like we see Venus or Mars, like dots of light. You would see them really as we see the moon.
Unlike in our solar system, the planets surrounding TRAPPIST-1 don't appear to have any moons, and its star is nowhere near as hot as the 1 million degree temperatures possible in the corona of our Sun. TRAPPIST-1 is classified as an ultra-cool dwarf star, and its mass is roughly equivalent to that of Jupiter. The lower temperatures allow the planets to orbit the star at a distance closer than Mercury orbits our Sun. But the lower temperatures don't necessarily mean that life will be present.
So ultra-cool dwarfs are known to be very active when they are young, and this is the main concern about these potentially habitable planets, that they could have been, the atmosphere been eroded strongly by the star when it was young. Now it's not very active, but maybe when it was young, the conditions were quite different. So it will be by observation that we will really figure out the past of these planets and what happened during this very active and young phase.
So this is one of the things that we're really questioning about these small little stars, M dwarfs. Almost all the stars in our galaxy are these small stars. And because they burn their hydrogen fuel so slowly, they last for a very long time. There is no M-dwarf star born in the galaxy that has yet died. Their lifetimes are measured in the tens of billions of years. So the star's going to be around for a long time. If you've got a planet orbiting that star, then there's a lot of time, perhaps, for evolution to work on that planet.
But evolution depends on the relative location within the system's habitable zone. In our solar system, Earth's planetary neighbors, Venus and Mars, mark the edge of our habitable zone. Venus's proximity to the Sun has made it an inferno of heat and volcanic activity. Mars, farther out, is an arid desert, boasting swirling red dust and frigid night temperatures. The TRAPPIST-1 system may be more forgiving.
So if we zoom out to the system away from the host star, you'll see all 7 planets, with the habitable zone indicated here in this blue region. The innermost planet in the habitable zone is TRAPPIST-1e. It's very close in size to Earth. It also receives about the same amount of light as Earth does in our own solar system. This means that in TRAPPIST-1e, you could have temperatures that are very, very similar to the ones that we have here on Earth. The next planet out is TRAPPIST-1f. Now this is a potentially water-rich world that is, again, about the same size as Earth. It has about a 9-day orbit, and during that time it receives about the same amount of sunlight as Mars does in our own solar system. And the final planet in the habitable zone of the TRAPPIST-1 system is TRAPPIST-1g. TRAPPIST-1g is the largest planet in the TRAPPIST-1 system. It's about 13% larger radius than that of Earth, and it receives about the same amount of starlight as somewhere in between Mars and the asteroid belt in our own solar system.
Well, with this discovery, we've made a giant accelerated leap forward in the search for habitable worlds and life on other worlds, potentially speaking. Because with not just one planet, but several, we have room that if we didn't have the habitable zone quite right or weren't sure quite what we're looking for, we have many chances over. Now, we don't know much about the planets. We know, as we heard earlier, the masses and sizes and their orbits. So for now, we just speculate. And for that, the TRAPPIST-1 system has really captured our imagination, because with this amazing system, we know that there must be many more potentially life-bearing worlds out there just waiting to be found.
Although Spitzer's monumental discovery is one for the history book, its original mission didn't involve searching for exoplanets. It was built to survey the universe using infrared light. The discovery of exoplanets was tasked to another one of NASA's observatories, the Kepler spacecraft. Since launching in 2009, Kepler has scanned over 150,000 stars, and in 2016 alone, identified a record-breaking 1,284 exoplanets, over half of its total haul of 2,476. 21 of these planets orbit their star's habitable zone, and are thought to be the adequate size for life to take hold.
And this has just been a revolution in astronomy and revolutionized our thinking about planets and the way they form and evolve. We now know of thousands of planets around other stars. And we see a wide diversity of systems, from planetary systems around binary stars, so two stars with planets around them, to planetary systems where you have Jupiter-mass planets right up next to the host star so that the temperatures on that planet must be very, very high. We see examples of icy planets, we see examples of rocky planets, we see a wide variety and diversity of planetary systems out there.
In 2011, Kepler observed what is known as Kepler 16b, the first confirmed planet orbiting two stars. The inhospitable world 200 light-years away from our Earth is roughly the size of Saturn and believed to be made up of half rock and half gas. And then there is our Earth's bigger and older cousin, Kepler 452b. Orbiting its star's habitable zone, the planet is 60% larger than our Earth and is 6 billion years old. But its distance, 1,400 light-years away, makes it impossible to image. Luckily, in 2016, the same observatory that discovered the TRAPPIST-1 system may have found a more accessible candidate, an exoplanet surrounding our nearest star, Proxima Centauri, may be the new Earth scientists are searching for. Proxima b is believed to be 30% larger than our Earth and orbits the habitable zone of its parent star. At a distance of 4.4 light-years away, it is still unlikely that we'll visit anytime soon, but it's not impossible. While current technologies are not yet prepared for a flyby, this could potentially become the first stop to exoplanet exploration.
What is so special, so fabulous, is that nature has given us one of these M-dwarf stars with a planet a little bit bigger than the Earth, and it's the closest star to us. It's Proxima Centauri. We can imagine building special purpose instruments, but we can take advantage of the fact that Proxima is so close to us that maybe we can image that planet. Maybe we can get spectral data. Maybe we can see the phases of the planet as it goes around in its orbit every 11 plus days. So maybe we can figure this one out.
Already there are theories abound. Proxima b has become a hot topic for planetary scientists worldwide.
If you lived on Proxima Centauri b, you would either have constant daylight or you'd be in the night all the time. You would have a night sky or a day sky. You can't go very far around the surface before you run into conditions that are no longer habitable. We'd be very interested to understand more about it, and it's almost within reach.
These questions about are we alone are being answered as we speak in this decade and the next decades. So I'm really excited about this.